This is a lecture on the introduction to network hydraulics. I am Professor Ali El-Bahrawy from Faculty of Engineering in Shams University. There are three types of hydraulic networks that we are going to study. One for pipe irrigation, and one for water distribution, and the third is for drainage collection. And each of the three types have different details that we are going to discuss together. This irrigation network of pipes under pressure takes water from the source at certain elevation and through two pumps pump water for sprinkler irrigation system to the terminal nodes numbered 5, 6, 7, 9, and 10. The other type of network is a water supply network with two reservoirs, two pumps, a pressure reducing valve, and certain valves. It's a completely different network with different purpose, but it also supplies water from the reservoirs through the pumps into the demand nodes shown in the network number 1, 2, 3, and 5. The third network is a collection network used for sanitary and wastewater, and in this network, as you can see, water is collected from the triangular nodes and ends up in the last node in the network number 10. But the collection comes from all these nodes with the arrows showing collection points. There are two types of flow, pressurized and gravity, related to the previous three examples. The pressurized network, as you can see, pipe will be full, the cross section is full of water, and in this example you can see a pipe, a pump, a valve, and a sudden enlargement with gradual section, and a pipe with a smaller diameter, and the lines you are seeing are the total energy lines, which is the solid lines, and the hydraulic grid lines, which is the dotted line, with the loss of energy throughout the system from the start to the other reservoir at the right hand side. For gravity pipes, you can see that water does not go in its direction due to differences in pressure, but due to difference in elevation, because water flows by gravity, and the section is not full of water. It is partially filled with water, as you can see in the two sections at the bottom of the graph, where the design variables here differ a bit, and they have to do, in addition to pipe diameters, they have to do with the slope of the pipe and the excavation depths. Another issue is network topology, which is the relation between nodes and pipes. And with respect to topology, we have two main categories: tree network and looped network. This is an example of a tree network where you don't have closed loops, and water is coming from node 1, and they are supplied to node 3, 4, 5, 6, and 7. For the looped network, you can see we have 4 closed basic loops where water enters at node 1 and it is distributed and to nodes 2, 3, 4, 5, 6 up to node 9. You can see here they put the node numbers between square brackets, and they put the pipe numbers into between parentheses. With respect to calculation of the network, to find the design variables or to calculate the flows and heads, there are three types of problems. Analysis problem that has to do first with the layout, pipe characteristics and nodal flows. Then another analysis to calculate the flows in pipes and corresponding nodal heads. The design type of problem, we have the sources and sinks with certain discharge, and we are designing the location of pipes and pumps and reservoirs and other elements of the network. The last type of problem is optimal design or optimization, and also they apply to the layout problem and the optimal combination of pipes and pumps to satisfy certain objective function, and in most cases it is minimum cost. Most of the hydraulics of networks are governed by two main equations. One is a continuity equation, and the second is the head loss in closed loops. We define continuity equation for a balanced network, and balanced network means flow in is equal to flow out. The external inflows from the sources is equal to the external flows from sinks. At each node, sum of inflow is equal to sum of outflow. In terms of energy equations, the head loss in closed loops, sum of the head loss in pipes with direction of flow is equal to 0. To solve the three types of problems mentioned in the previous slide, we can use different variables. We can use flow or Q, we can use head or H, or we can use corrective flow delta Q or corrective head delta H. To show you how the four variables in the previous slide is expressed in terms of equations, you can see the first one, head loss is a constant multiplied by Q raised to power n, and Q from node 1 to node 2 in terms of H is calculated in the second equation. And the last two equations shows us how to use corrective flow and corrective head to calculate the continuity equation and the energy equation shown in the slide. We are going to use a sample network of one loop with one source and two sinks and node 3 without outflow, and we give the nodes names between parentheses, and we give numbers for the pipes, as you can see, 1, 2, 3, and 4. The following slides will give 4 different applications of the 4 types of equations for the sample given in the previous slide. This slide shows how we solve the analysis problem for the one loop network using Q as discharge, and we have the energy equation, which is here. The last equation is a nonlinear equation. One simple solution to this system of equations, because the number of linear equations is in most cases greater than the number of nonlinear equations, is to linearize the nonlinear equation in the form in the last line here, and then this will update the constant, and we do iterations until we arrive at the solution. This slide shows how to solve the same problem by using H as variables and the equations you see here are three independent continuity equations at the nodes 1, 2, and 3. Because the network is balanced, we don't need a fourth continuity equation because we solve three independent equations for the variables H2, H3, and H4. Here we use the delta Q system where we write only one loop equation in terms of delta Q. And because this is only one loop, it has a name in hydraulics. It's called the Hardy-Cross delta Q system, and we need also iterations to arrive at the solution. Here we have three continuity equations in terms of delta H for three different variables: delta H2, delta H3, and delta H4. And we use the correction if we want to correct for single nodes. We use the delta H equation in the last line, but if we like to have a solution for the whole system by solving a system of nonlinear equations, we choose the three equations at the beginning of the slide. How to solve the equations in the previous 4 slides? We have two types. If the equations can be linearized, we can solve a set of linear equations. But most of the equations are nonlinear, and we use what we call Newton-Raphson, and we are going to show you the algebraic details of how to solve these systems of equations. A system of linear equations is shown here, where the first equation is a11x1 plus a12x2 up to a1n xn equals b1. We have coefficients for the variables x1 to xn, and we have right-hand side b1 up to bm. How we solve this? We solve using algebra first by considering vector equation, that is writing the above equations in terms of vector notations in the end of the slide. Then we transform the previous form of equation into matrix equation, where A is a matrix of coefficients, and X is an array of variables, and B is an array of right-hand sides. By doing that, we can calculate X by inverting the coefficient of the coefficient matrix, and we can get X as A minus 1 multiplied by B. Therefore, to solve the set of equations, we need to invert the matrix of coefficients. With respect to nonlinear equations, the equations, we make the right-hand side 0, and we have a set of equations like you can see, and they can be rewritten in compact form as f of x equal 0. Here, to solve the problem, we use the Newton-Raphson, where we calculate the f of x naught plus delta x naught is equal approximately, due to the Taylor series expansion, into f of x naught plus j naught multiplied by delta x naught, where j is the Jacobian matrix. The Jacobian matrix is a square matrix that differentiates the first equation with respect to the variables. Therefore, we have in the first row of the Jacobian matrix partial f1 by partial x1. The second term is partial f1 by partial x2, until we reach the last row, where the last element to the right is partial fn by partial xn. This equation has to be calculated by differentiating the functions, and because we seek to make f of x naught plus delta x naught equal to 0 by adding this correction, delta x naught can be calculated as the inversion of the matrix, Jacobian matrix J multiplied by fx naught. If we do that, we can calculate the first iteration or the first value of x1 as x1 equals x naught plus delta x naught, and in general form, because we have different iterations, we calculate x to the power nu plus 1 in the form shown. Spreadsheets are powerful tools to do such calculations, both for the system of linear equations and for nonlinear equations. Why? Because in both cases we need to either multiply a matrix with an array or invert a matrix. And Excel can do this very easily using two famous functions. One of them is mmult to multiply two matrices, and the other one is m-inverse to invert a matrix. Another important issue is how to name pipes. For tree networks, the naming is very easy because of the direction of flow is known before we do the analysis problem. Therefore, distribution, downstream node, and collection is upstream node are used to name the pipes, because we don't need to have different names as in looped network. But for looped network, the only way we specify a pipe is to decide the origin destination pairs, which can change according to the external conditions. This is an example that shows you for the distribution source is 1, and it sends water to the nodes 2, 3, 4, 5, and 6, and therefore the name of the pipe is the name of the downstream node. If we collect water in node 6, therefore we call the pipe by the name of the upstream node. As you can see, pipe 1,4 is called 1, pipe 2,4 is called 2, and so on. Another problem is the location of pipes on plan, which is called the layout problem. But this particular problem has a separate design and optimization models, different from the analysis design and optimal design for the previous network. And the network layout is simpler than that for the looped network. The tree layout is simpler than that for the looped network. The main concern for the looped network is the level of service reliability, and the reliability is an important issue in water supply systems. Usually, if you have one source and different sinks, we can transfer water to the sinks using a tree network, but this will have no reliability level. Why? Because if one of those three pipes is broken, some sinks will not receive water. This is why we add redundant pipes. Redundant means in addition to the three pipes, to improve the reliability in case of pipe break. And when we increase the number of these redundant pipes, the reliability level will be enhanced and increased. This is an example showing that the source is 1, and the tree network that takes water to nodes 2, 3, 4, 5, 6, and 7 are shown as continuous lines, and the redundant links are shown as dotted lines. When we increase the dotted lines, we increase the reliability. By doing that, if you can count with me, the basic closed loops will be 1, 2, 3, 4, and 5 closed loops, which is the same number of the redundant links as we will see in the topology section. Direction of flow is another issue. For tree network, direction of flow is known before analysis or optimization, but for looped network, the direction of flow changes with every analysis problem. When pipe diameters change, external flow change, we cannot decide on the direction of flow in pipes before analysis, like in the case of tree network. This is a simple exercise where we have 11 sources and one sink, and this is a collection network, and we wanted to know the direction of flow, and we like to name the pipes from the previous knowledge in the shown and the description and explanation made in the previous slides. Here we know the direction flow in the tree network, where we want to transfer water from the source 1 up to the nodes 2, 3, 4, 5, and 6. But when we add the redundant links shown by the dotted lines, the direction of flow may change, as we mentioned before. The topology of the network allows us to make simple calculations of the tree network. The number of pipes will always be the number of nodes minus 1. And for loop network, the number of independent loops is the same number of redundant pipes. And the number of redundant pipes will be the number of pipes minus the number of tree pipes. And we can check the previous network to make sure that these relations are valid. This is a simple exercise for these two loops network, and we wanted to apply the equation that we learned in the previous slide from topology of network to find the number of nodes, number of pipes, and number of loops, and apply the equations of topology mentioned. How to calculate the pipe flows? For tree network, it's simple calculation because we go backwards and then until we reach the source. But for the case of loop network, we need to solve a simultaneous set of equations as we shown in the slides above. This is again another simple example for a pipe irrigation network shown in the very first slides of the presentation, where we are asked to name the pipes and to calculate the pipe flow if every terminal node withdraws 4 cubic feet per second. Again, the terminal nodes are number 5, 6, 7, 9, and 10. Here also the spreadsheet can help us calculate the tree flow calculation. Even though it is simple, but sometimes the network has too many pipes and calculating backwards is a bit intricate. Therefore, we can use a famous function in Excel called SUMIF, and the next slide will show you a snapshot of the calculation of the pipe flows in the previous tree network. This is a calculation of the pipe flows in the previous exercise, and I'm showing you here how SUMIF function is used to calculate the pipe flows automatically using the solver optimization model, where I show you here the target cell, and the function is to minimize and the variables that change and the constraints used for the calculation. It's a bit complicated, but it's a simple exercise that allows us to calculate the tree flow pipes. This is the last slide, where we like you to summarize the whole lecture in terms of a matrix to compare between the different aspects of network hydraulics in terms of layout, variables for calculation, solution techniques, and other aspects. I hope you enjoyed this lecture, and it is of some value to those of you who are interested in hydraulics of networks.